part of this lecture, of this climate change predictions. Okay, so starting a little bit with a note of caution. Okay, as I said, my experience is that there's many more traps in this than I initially thought about it. So when I started out 20 years ago, I thought that climate change is all settled, it's all known, we don't need to do any research on it. And first 10 or so years, I didn't do any research on climate change. But then I noticed that in the details, things are much more complicated and much more interesting. So therefore, there's lots of research that can still be done. But I start with showing you the traps that there are, I think. And this is helpful to understand that there's still lots of interesting research to be done. Okay, the first trap is the warming pattern. And I thought that this is well understood. So the warming pattern, if you look at this is the winter, northern hemispheric winter and northern hemispheric summer pattern as it is predicted by the IPCC models. So, and I think the main thing that most of people see here, that the land warms more than the oceans, and the biggest warming here is in the Arctic in winter. And I think this is more or less known for about 30 years. I think as long as I know about climate change, in the 1990s, this was basically always a pattern that looked like this. And obviously you would think this is a well understood pattern. But this is not the case, unfortunately. I think I figured out that this is actually not fully understood. And just I'd like to point out two things here. First of all, so the question is, why do we have this pattern? And think about the one thing is the biggest warming is in the Arctic in winter. And when you read about it, a lot of people say this is related to ice albedo feedback, which does not make much sense because there is no sunshine in winter in the Arctic. Right? How can this be ice albedo feedback when it's the Arctic in winter and there's no sunlight? That already tells you that even this most dominant signal, I mean, it is related to the ice albedo feedback, but this is not the whole story. There's a lot of other things playing into this. And it's much more complicated than you think. But I always thought, when I saw this, that this is well understood and it's well documented, but it really wasn't. It's really just in the last 10 years that people wrote more publications about this, and this is now a little bit better understood. But about 20 years ago, when this was already known, nobody really looked into the detail of why this pattern exists. So even the Arctic amplification is not that trivial as I always thought it is. And there's still research being done on how this actually works. And another example that I already talked about this a little bit on Monday is that the land actually warms more than the ocean. And again, if you look into literature, many people say that this is trivial because the land responds fast and the ocean is kind of slow and it lags behind. But this is not the case, right? I mean, this is the case, the land lags behind as the ocean lags behind the land. But actually, even if you wait forever, the land will always more warm than the ocean. So in equilibrium, then ocean is well settled into its state, the land warms more than the ocean. And the first paper on this is from Sutton et al. In 2007. It's not really the first paper. If you go back 20 years, there's some other people mentioning this before. But really, in 2007, he wrote a paper exactly saying that the land warms more than the ocean in equilibrium. And that really made me think about the whole stuff again, that we have been looking at this pattern for a very long time, not really knowing what was going on, and nobody really cared. And in 2007 is the first paper that really addresses this. And that is when I started also to do research on climate change, because I recognized this before. Actually, I recognized this somehow in 2006, that the land warms more than the ocean in equilibrium. And for me, it was a big surprise. But obviously, it was not well known, but I thought it was well known. So a famous experiment that really illustrates this nicely is an experiment which was famous from Seth et al. In 1990, but they didn't really discuss the implications. They just did this as a climate change exercise. So the simple experiment is that you take your ocean and prescribe it to the atmosphere, and you warm it by 1 degree, and let the atmosphere respond to it, and the land surface temperature respond to it. And if you do such an experiment, here's my version of it. So color bar means white is 1 degree, and everything which is yellow and red is more than 1 degree. So if you warm the ocean everywhere by 1 degree, you will see that the land respond to that by warming more than 1 degree, which to me was a huge surprise. I didn't know that this was going on. So I did this experiment myself in 2006, and I was totally stunned by it. And I didn't really know how this is working. And I still don't know exactly how this is working. I know some elements of it, but I'm not completely understood how this is actually working. But I can show some elements of how this is working. But I find it really a big surprise that when you warm the ocean by 1 degree, that the land warms more than 1 degree. So that's when I started to do climate change research. So I think this warming pattern already illustrates you that even this warming pattern is known for a very long time. It isn't really fully understood in all its detail. And I think it's important to understand these things. And really, people started to work on this more or less just, I think, the last 10 years or so. People think more about these details and started to do more research on that. Okay, here's another example. The second example is something which is very important for the east coast of the United States and for Europe, which is the North Atlantic Oscillation. So in my generation, everybody who did his PhD in the 1990s, they know something about the North Atlantic Oscillation. So the North Atlantic Oscillation is basically this position of the storm track having a low pressure here, high pressure here, and this varies a little bit, this low pressure and high pressure, and this is called the North Atlantic Oscillation. And it controls more or less the weather in Europe in winter and also on the east coast of the United States. And if this is strong, then you have strong winds blowing from the ocean to Europe, and then it's in winter fairly mild and moist here, and dry and relatively cold here. And that is fairly important for the weather prediction in Europe. And there's a very famous paper about it. And this is the Hurl et al. In Science 1995, which was really, I think, for my generation growing up in Europe, it was very groundbreaking. And you can see the number of citations that is a very highly cited paper. And here's a statement from this. And maybe I just read this, because this statement is kind of, I think, it makes you think about it in a certain direction. So in the past decades, we sampled some results obtained by coupled atmosphere-ocean models forced with steadily increasing atmospheric greenhouse gases. So they're saying this looks like climate change simulations. So you have climate change simulations, and it resembles this. Decadal variability in the NRO has become especially pronounced since the 1950s. So 1950s are here. And you see he's talking about this change here. But the cause of such variability in the Atlantic are not clear. The relation of the NRO to greenhouse gas forcing and possible links to coherent variations in the tropical Atlantic SST need to be examined. So he's suggesting, or he's indicating, but not really making any statements, that this might have something to do with greenhouse gases. So this is a very vague statement, and he's not really saying anything, but he makes you believe something. And I think what most people in my generation try to think about this, when they look at this, they see something like this. They see an increasing trend. Right? I'm pretty sure to everybody who I talked about, and I know a lot of people base their career on this, that this is an increasing trend in the NIO. And this was in the 1990s. You would think that the NIO should be up here somewhere now. Right? If you read this paper and you see this, and you have been in the 1990s, you would think the NIO is up here now. So I updated the figure. This is the NIO, and this is now the last 10 years or so. And this is what you thought initially would happen, but nothing happened. No change at all, right? Not even decadal. It's just pure noise. There's nothing happened at all. But clearly this paper, I think, why it's been cited 4,000 times is because people thought that something like this might happen. But it didn't. Right? And I think it's a big blow for many people who work on this, that this didn't happen. Right? Nothing happened with the NIO. It's just random noise around normal. And I think we are all kind of looking into one direction right now. Everybody thinks that whatever happens when there's a trend is climate change. Right? But not every trend is climate change. Right? Some things just happen, and we tend to see something that doesn't really exist there. Okay, so these are my two examples of note of caution. So first of all, I think you have to be really careful, because we all think in the same direction, and this is dangerous, right? Because not everything that we see is actually what we think it is. So not everything that looks like climate change is actually climate change. And be very careful about this. Even though you have 10 Nature papers telling you that this is climate change, it doesn't have to be true. Right? Because we are misleading ourselves a little bit in this. Not everything that the climate models predict is really understood. Even though, I mean, if you have heard it 10 times and everybody agrees on it, that doesn't mean we really know why it is this way, right? So a lot of things I think the climate models predict might actually happen, and they all are agreeing on it. There's no uncertainty in it, but it still doesn't mean we know why. We know how it works. And not everything that the climate models predict is true. So unfortunately, there are errors in the models. Right? We don't know yet what it is, but there are some indications that not everything that they predict is correct. So there's large uncertainties, and I will illustrate you some of them later on. And also the other way around, if a climate model predicts that there's no change, that doesn't mean it's not changing. Right? There's some things that the climate models predict to be not changing, but actually they are dramatically changing. So there are things happening that we haven't really on our radar right now. So keep this in mind, whatever I'm talking about, and I will highlight a few of these things, but sometimes you may think, at least this is what I saw, that things are better understood than they really are, and that there are some things really varying in terms of uncertainties in the models. Okay, let's go through the three main things here. So first one, the warming pattern. And we talked about this a little bit on Monday. So I would like to know how this warming pattern works. So why does a doubling of CO2 everywhere leads to different amount of warming at different locations? Okay, so getting at this, you can basically simplify your climate or whatever you're looking at. So let's say you have an approximated energy balance. Let's say this is my energy balance, so heat capacity, change in temperature over time. So this is a change in energy, so my energy balance. And if you think about this, let's say being the temperature anywhere, so you have a feedback term usually, C being a negative feedback. Let's say constant. This is just a simplification of whatever goes on. So it's a linear feedback and a forcing. You can basically simplify the whole system into something linear. It's just an approximation to make the calculations simple. So if you want to know how your system is responding, then your response, your delta T, is your forcing divided by the feedback with a minus. So feedback is always negative, so you have a positive forcing divided by something negative, and negative gives you a positive warming. So if you want to know how strongly it responds, you need to know how strong is the forcing and how strong are the feedback. These two things define how strong your response is. And the strength of both of these things can vary with location and season. Right? And I will show you that this forcing, even though we are doubling the CO2 everywhere, is not the same everywhere. The forcing is different at different locations, and the feedbacks, they are different at different locations. And that gives you then the effect that the response looks different at different locations, even though we have doubled the CO2 everywhere. Okay, so I will go through this step by step. So I start out simple, and then we go to the fully complex response. And I do this again with the grip model that you have used on Monday. So the grip model creates this warming pattern, which looks very similar to the very complicated models. So the land warms more than the oceans, the tropics warm less. You have more warming at higher latitudes. And you have, in principle, you have the strongest warming in the Arctic. This model doesn't quite do that. So the Arctic amplification is not as pronounced in this model as it should be. But it's roughly there a little bit. And then we have these little processes being involved in this. And I go through this now step by step, starting out simple and then creating eventually this complicated pattern. Okay, so a starting point is we make the word simple. So we assume, first of all, no feedback. So no water vapor feedback, no albedo feedbacks, nothing is responding. The topography, I erase the topography. There are no mountains. Circulation, I also do not allow. So each point is responding initially individually. There's no interaction between locations. And I assume that the cloud cover is everywhere the same. So an average 70% cloud cover. And I assume the water vapor is everywhere the same, a global average water vapor level, which means in the tropics there's less than we observe today, and in the polar regions there's more than observed today. So just to erase the effect of different amounts of water vapor at different locations, and erase the effect of different cloud cover at different locations. So everything is fairly simple. Every point more or less sees the same thing. Right? There's no differences in different points, but the background climate temperatures are different. So we have still the observed correct surface temperatures. So if you do this, then the global warming looks like this. It's more or less everywhere the same. And you see the color here is roughly 1.5 degrees of warming. And if you can see, there's a little bit more warming in the tropics than in the polar regions. And that is because this black body radiation is T to the power of 4. So the warmer regions will have a slightly stronger warming than the colder regions. But it's just a small effect. You can more or less neglect that. You can more or less say, if everything is, there's no other thing or structure, then every point will warm the same amount, which is what you would expect as saying if you do a doubling of CO2, you would expect every point to respond the same way, and this is what they do. Okay, so initially there's no structure, so everything is more or less the same, and the warming is moderate. It's just 1.5 degrees. And later on you have much more warming. Right?
Why is, if there's no topography, why is it slightly cooler along Chile?
Because it's cold there. So there's a mountain range. So I keep the temperatures as they are observed. So in principle, there's a mountain range here, and I took away the mountain, but I kept the temperature as they are observed at the surface, and they are on a high mountain, so they are cold. So these cold places like Tibet here, mountain ranges here, they are still cold, like Antarctica, which is very cold. I don't calculate the temperature back to sea level or something. It would be complicated. Okay, so the first thing that we introduce now is topography. And topography does what are more or less the obvious. The higher the mountain, the less of an atmosphere is on top of it, and the less of a CO2 effect. So you would expect where there's mountains, there's less of an effect of CO2. And that you can see here, if you compare the previous one with the new one, you see those mountains like Greenland or Antarctica or Tibet, they now warm less. And I show you the difference plot, so the difference between this and this is shown here. So all these mountain regions are now warming less because they have less of an atmosphere on top and therefore less of a CO2 effect. You can go to the extreme and make the mountain go up into space, then there obviously can't be a CO2 effect because there is no more CO2. Okay, so the mountains warm initially less. Later on, due also to the feedbacks, they will warm more, but initially just the forcing is less over mountains because there's less of an atmosphere. Okay, the next step, I introduced clouds being different at different locations. So initially clouds were everywhere the same, but now we have some locations with less clouds and some locations with more clouds as it is observed. And then you can see this introduces quite a bit of difference. So now those regions which don't have many clouds are warming more. And that is because clouds have a thermal radiation effect and that interacts in a linear way with the CO2. So those radiation that the clouds are already emitting, that the CO2 can't have much of an effect on it. So the difference plot is exactly those regions that have lots of warming now are the regions with little clouds, and those regions which have less warming now are those very cloudy regions, like the Southern Ocean, Northern North Atlantic, or North Pacific, or here along the equatorial convergence zone. There's a little bit of less CO2, effective CO2 forcing due to the cloudiness. Okay, and then the last element that plays into this direct forcing effect is the humidity. So now we make the humidity being more humid in the tropics and less humid in the polar regions. So now we have humidity unequally distributed, and that also has an effect. You can now see that the humid regions, like here the warm pool, the Indian Ocean, has more water vapor in the atmosphere, and that makes the effect of adding the CO2 less important. So it does not respond to the CO2 as much. So the difference plot between these two looks like this. You see all the humid regions are now warming less, and all those relatively dry or cold regions have less water vapor in the atmosphere, so these dry regions are more sensitive to the CO2. So you can already see that the difference between tropics and polar regions is already in the forcing. Right? So the forcing leads to more warming in the higher latitudes and less warming in the tropical regions. So we can summarize this just from this equation. The forcing is already different at different locations effectively because of the forcing interacting with cloud cover and humidity and topography. And that gives you this pattern here that you can already see the forcing is stronger over land than over the tropical oceans, more or less. So there's a little bit of structure already in that. And you see this varies between about 1 degree warming and this one here about almost 2 degree warming. So this is almost a factor of 2 already in the initial forcing without any feedbacks being involved in this. Okay, so we had basically focused on this first part here now, the differences in the forcing. Now the next steps are focusing on the differences in the feedbacks. Okay, but before I put on the feedbacks, I turn on the circulation. Now I let heat being transported around. That smoothes out everything. So you can't see this. This initial thing was really the local point-to-point and no interactions. Now we have everything interacting and everything is smoothed out again. So you can't see really the structure. But I do this to have the feedbacks being active and don't look so noisy. Okay, so let's put in the first feedback. And the first feedback is that the ice cover might change in the future, and that has an ice albedo feedback. So it means if the ice shrinks, there's more dark surface, and then it heats up more. And over ocean, if the sea ice disappears, the effective heat capacity is changing, and that also has an effect. Probably this is a very important effect in the Arctic region. Okay, so if we do this, we get a strong enhancement of the warming, in particular in the northern hemisphere, on the continents in Asia and North America. And the difference plot I've shown you here. Maybe I should point out the color bar here is nonlinear. So I'm trying to highlight even the little changes here, which are really tiny, and then the big changes. So you can see when I highlight this in a nonlinear way that this increase of ice albedo feedback, which really is just more or less in the northern continents and around Antarctica, but it does affect also other regions which don't have ice and sea ice, which is due to the transport of heat around in the system. And you can see this is about an effect of about half a degree extra warming here in the northern continents initially, but then later on there comes another feedback on top of it. So it depends a little bit in which order you are switching on your feedbacks. If you switch on this feedback after you switched on the water vapor feedback, then this effect is bigger. So it depends a little bit on the how you are actually introducing these elements. Okay, now I put on the water vapor feedback. But I do this in two steps. In the first steps, I do not allow water vapor to be transported into different locations. So I just look at the local water vapor feedback. And you see it does a big bang here, so it basically doubles everything. So suddenly everything it's much warmer. So much of the warming, so initially we had here a warming of about 1.6 degrees or so, and then suddenly we have 2.5. So it's almost a doubling of the effect, the water vapor feedback. Not quite, but it depends also on different models. It might be different, but in this model, it's more or less a doubling of the warming. And it's more or less everywhere the same. There's almost no structure. And it's only Antarctica that sticks out here, which is a mountain. I think that is somewhat particular, but otherwise it's always the same. And I wouldn't trust my model on Antarctica here, so don't take this serious. I'm not sure whether this makes sense or not. Because it's a very specific location. It's a high mountain, very small region in the polar setting, so I'm not sure whether this is correct or not. Okay, so in the next step, I allow water vapor to be transported around, and in two steps. First of all, I diffuse it, so by turbulent mixing. And when you look at the difference, this is shown here, that what the diffusion does, it takes water vapor away from those locations which are moist and brings the water vapor onto land, basically, or mountain regions here, or higher latitudes. So basically, it takes it away from moist and wet to dry and cold. And dry and cold tends to be the high latitudes and the land. And you can see this already gives you the structure that we have seen in the beginning, that the land now tends to warm more and the high latitudes tend to warm more. And in the second step, when I follow the advection, so I follow the mean wind flow, that has a similar effect, but it's more dominant on the northern hemisphere. So then you again take away the water from the moist and warm regions and bring it onto land, following the mean flow of the atmosphere, and that gives an additional enhancement, particularly in the northern hemispheric continent and the Arctic region. Not so much in the southern hemisphere, so there's a little effect there. So you see that this contrast between land warming more than the ocean is partly due to this transport of water vapor onto land. Okay, the last thing I put in here is the ocean heat uptake. And that is basically a transient effect. So if you look at this after 50 years, you don't see much of a difference. So this is a transient effect. But when you look at the difference, it actually affects almost every point. Right? It's not just an ocean thing cooling and the land not, but it's more or less everywhere. And really, it's a transient thing. So I show you the time series from start 0 to 50 years, and this is the global mean temperature here. And the model without the deep ocean heat uptake or the deeper ocean heat uptake, it responds fairly fast, and then it goes in equilibrium, while this one, with the heat uptake in the subsurface ocean, it slowed down, and eventually it gets to the same level. So if you wait long enough, these two will be the same in the global mean. But if you compare land versus ocean, so red curve is the land temperature in my fully active model with the ocean heat uptake in there, and the blue is the ocean temperatures. And you can see the land stays always on top of the ocean. It warms more than the ocean. It's not a transient effect. It is always warming more. So here I plot the ratio between land and ocean. And you can see initially when you switched on the doubling of CO2, there's an initial fast warming of the land, and then eventually land and ocean getting into an equilibrium. And that equilibrium is larger than 1. It's about 30% more in this model. In some models this is bigger, in some models this is lower. In this model, it's about 30% more warming over land. Due to these different elements, the forcing being different, and feedbacks being different, and water vapor being transported onto land. Okay, summary of the warming patterns. So there are regional differences in the effective forcing of CO2 and the feedbacks, and these lead to regional differences in the response. Cloud, humidity, and topography are effectively interact with the CO2 forcing, and that gives you different forcings. The water vapor feedback doubles the warming, more or less. And there's a number of aspects that leads to the land warming more than the oceans. And I didn't talk about the Arctic amplification because I don't trust my model that much, and it's a fairly small location, so I didn't say much about that. Okay, so next point, atmospheric circulation.
So what's the water vapor feedback? Just precipitation, evaporation?
So the water vapor feedback is that the warmer air can hold more water vapor due to Clausius Caperon. So if you have a 3-degree warmer atmosphere, you have 20% more water vapor in the atmosphere. And since this is the most important greenhouse gas, this leads to additional, more thermal radiation going back down to the surface. That's the water vapor feedback. And in this model, it's about a factor of 2 more warming.
And so, that warming of the land, is some of that due to latent heating or precipitation? If you're diffusing over land?
Yeah, that is it. So, let's, for example, latent cooling at the surface mostly happens over the ocean, while latent heating happens in the atmosphere, which is really. So, basically, what you do is you evaporate the water due to more. If you have more precipitation, you are evaporating more, and that cools the ocean. But then the heating takes place in the free atmosphere, and that is fairly well mixed. So that happens basically everywhere at the same time, and therefore it warms the land effectively. Okay, atmospheric circulation. So we talk about these large scales here, and I don't know if you had.
You've been catching the 370?
Yes.
Yeah, no, well, like the 370 is a nightmare. Yeah. Oh, what a shame that you missed. It's a really good half-hour lecture. Yeah. 370 is not to be trusted.
I'll give you a short summary of what you have missed. You should be cautious about this stuff, what I'm talking about. And there's a warming pattern due to different regional forcings. So that means the CO2 forcing is not everywhere the same strength because of clouds, humidity, and topography. And there's feedbacks that are different over land and oceans that makes the land warm more than the oceans. Okay, now at the atmospheric circulation. So when I talk about atmospheric circulation on the large scale, we have this idea that there are large circulation patterns. And I start at the equator. Typically, the air rises here at the equator, and then it moves away from the equator, it sinks somewhere and comes back. This cell here is the biggest cell, the most important cell, and it's called the Hadley cell. And they are both on the southern hemisphere and on the northern hemisphere. And then back at the surface, this air flows back in these so-called trade winds. That means they are mostly easterly winds and from the north towards the equator. So this cell is the biggest circulation cell of the atmosphere. It's called the Hadley cell. And then there in the polar regions, in the extratropical regions, there's a spheral cell, which is a more complicated one, which is more turbulent. We somewhere live look at this interaction between the Hadley cell and the other cell. This is our locations, basically. And forget about the other cells. So I will mostly talk about the Hadley cell. And another cell that is not shown here, this is a meridional cell along the equator, which is called the Walker circulation. And I will talk about these cells mostly. Okay, but first of all, maybe mentioning something here. So there are many different aspects that will change in the future in terms of atmospheric circulation and its variability. There's way too many that I can mention here, but I mean, can talk weeks about this, I think. Maybe just some points. So some of them are really well understood, and they make sense, and they are straightforward, and you know what's going on, I think. And most are not fully understood, I think. There's a lot of stuff that goes on, and all the models predict the same, more or less the same thing, but we don't yet fully understand of why that is or how this works. And then there are many things that are fairly uncertain. So there's also lots of stuff going on which we don't know really. And I will show you some examples actually with the Walker and the Hadley cell that are not fully understood. Okay. But maybe thinking that we all think about climate change, let's go back a step and think about climate is not changing. So you have global warming, everything gets warmer, but that doesn't mean everything is changing. So even a 3-degree world is more or less the same world as today. And I just want to highlight this here, maybe in showing you a figure. So this is the global surface temperatures in the normal world, let's say 21st century average. and this is 20th century average, and this is the future with 2 times CO2 average. And if you look at this, you may notice some differences, but just focus on the pattern and the gradients. And do you notice any differences in terms of pattern and gradients? Not just that the other one is warmer than the left
A
one.
stronger gradient between the low latitude and high latitude.
You think?
I think so. If you look at Antarctica and then you look at the, say, for the equator and the Atlantic, it seems like the gradient is strengthened.
In this one?
Yeah.
So gradient strength means the color is changing faster, right?
Yeah.
So this looks wider to me than
I
this
feel
one.
like in total, though, between, say, 0 and 8 degrees.
Okay.
There's a weighted gradient plus
You think? So you say it's a weaker gradient from here to here? Yeah? Maybe.
So much difference.
That's a key point. That's the key point I wanted to make. There's not much difference, right? I mean, to me, these patterns are very, very similar, right? And for atmospheric circulation, that matters, right? Atmospheric circulation is driven by temperature gradients and by the pattern, right? So if the patterns are about the same, your first guess is nothing is changing, right? And that is a good guess. I mean, if you think about this, first order is nothing is changing. Keep this in mind. The pattern is not so different, right? It's not widely changing. I mean, it's warmer, but the patterns is about the same. And therefore, your first expectation should be not everything is changing. Nevertheless, some things are changing. But just keep this in mind that not everything is changing. The pattern is more or less the same. There are differences, and maybe you're right with what you pointed out, but they are not dramatically different. Okay, so I focus now on 2 things. This is the Hadley cell and the Walker cell. And even though there are lots of other things you can talk about, I just talk about these 2 because we don't have that much time. Okay, I showed you this before. So the Hadley cell is this big cell here, the meridional circulation, and it's driven by the heating, basically. So it's a direct heating cell. You have heating at the equator. This makes the air rise, and then it sinks somewhere else. And it has a certain width. So how far does this cell go? Why doesn't it go further to the poles? So you might ask your question, what determines where this cell ends? And I don't really know, but it has obviously something to do with the physics. So how fast is the Earth rotating? So if you have an air passer starting up here and then it moves towards the equator, then Coriolis will deflect it, and then eventually the cell will collapse. And baroclinic instability is one element playing into this. So at this location here, they are the higher level jets, and they are baroclinically unstable, so they tend to go into turbulent motions. And what sets this instability is it's complicated, and I don't go into this. But there's a potential that this, the width of this cell, so how big this cell is somewhat depending on the climate state. So if the climate state is changing, you can imagine that the width of the cell can change, or the height of the cell can change. And that is what is being predicted and what's happening. And maybe just to illustrate this again, the Hadley cell, if you make, so this projection of the Earth is showing an area conserving way of the Earth. You see the whole Earth, you see Australia here, and you see the size of the Hadley cells, basically, which is illustrating that they are pretty big, and it's the most dominant part of the Earth's atmospheric circulation. And we are here somewhat at the end of the Hadley cell. So if the Hadley cell changes its width or its position, it does have an impact on Australia. Probably more than in any other country. Maybe South Africa would be similar, but it's fairly important for us what the position of the Hadley cell is. If you live in Europe, you probably don't care that much about that, but in Australia, you should care about this, I think. And also with the other cell, which I show later on, the Walker circulation cell. The Walker circulation cell more or less goes from here to here, and that also influences our climate a lot. So this is why I pointed out these 2 elements, because they are fairly relevant for Australia, I think. Okay, so one way of illustrating what might happen to the Hadley cell is this warming pattern here. And I'll now show you a warming pattern in the vertical, basically. So we have here on the x-axis the latitudes, equator, southern hemisphere, northern hemisphere, and then we start at the surface and we go up to the end of the troposphere and then into the stratosphere. And the warming pattern looks like this, that there's this big warming blob in higher levels over the tropics, and then there's this warming blob at the Arctic polar region. And there's a number of things that you can think about it which influence atmospheric circulation. So atmospheric circulation is driven by temperature gradients. So you can first of all think about the surface temperature gradient. the surface temperature gradient here, the meridional in the northern hemisphere, it's less warming at the equator and more warming in the polar region. So this changes the meridional temperature gradient, which is relevant for creating, like if you think about thermal wind balance, it would create the winds at higher level. So this should influence the winds at higher level. But on the other hand, in higher levels, the tropics warm more than the Arctic. So it's the other way around. Makes things complicated. And what you can also notice is that the surface warms less than higher levels. And if you think about atmospheric circulation, you have a surface and a higher level warming more. This is stabilizing the atmosphere. So usually if you have warm below cold, this would destabilize and set things into motion. But if you have something warmer over something cold, this stabilizes it because warm air likes to be on top of cold air, so this is a stable situation. So there's a tendency of this being illustrating that the atmospheric circulation might be stabilized because it warms more at higher levels than at lower levels. So this indicates there are things that leading to changes in the circulation a little bit, because there are some gradients in these. There's meridional gradient at the surface, there's an opposite meridional gradient at higher levels, and then there's vertical gradients in warming. And these things lead to changes in the circulation.
Sorry. Steve Sherwood in the first day showed us just a really quick graph of the troposphere and then sort of the gradient of temperature from the surface to the tropopause and then the kink in the stratosphere.
Yeah.
So in that case, this has just changed, right, in temperature?
This just changed, yeah.
So does that mean, how does that fit with that?
So did he show absolute temperature or changes in temperature?
Absolute temperature.
Yeah, so it basically means, so temperature usually, so if I plot just the average, so temperature at surface would go down, so if temperature goes this way, say here's warm and there's cold,
yeah.
It cools down and then it goes up again, right?
Yeah.
And now you have more warming here, it means this turning point is shifted a little bit. So it basically means that the troposphere is lifted a little bit in the tropics,
Yeah, okay.
and then the stratosphere starts a little bit later.
Okay.
And then there's cooling in the stratosphere here. So the stratosphere gets even cooler.
Okay.
I'm not that much an expert on this higher level, what happens here. I don't fully understand that. But I think it's well known that there's more warming in higher levels in the tropics. There's more warming, there's a change in meridional temperature gradient on the surface, and there's an opposite meridional temperature gradient in higher levels. So these are the key features, I think, that are well predicted. And they should have some implications on the change of circulation. So here's the Hadley circulation changes as predicted in the models. So on the x-axis, there's an index of how the circulation changed, so the boundary of the Hadley cell in terms of latitude change. And red dots mean northern hemisphere, blue dots mean southern hemisphere. And then if it's positive on the northern hemisphere, it means it goes further to the pole. That means a widening of the Hadley cell. And you can see most of the models show that the northern hemispheric branch of the Hadley cell goes further to the North Pole by about 1 degree in 80 years, which is not that much, right? It's 1 degree further to the poles in about 80 years. And the southern hemisphere, which is more interesting for us, is also similar. It goes 1 degree further to the South Pole, and most of the models do that in about 80 years. So the Hadley cell gets closer to Sydney and Melbourne. Right? It's the southern branch of it. And the y-axis shows another index which shows the displacement of dry zones, which is another way of illustrating this. And it does basically the same thing. Right? So the southern branch goes further south, and the northern branch goes further north. So it's a widening of the Hadley cell. That is all good. Unfortunately, the observations tell you a different story. So there are publications of the last 30 years about trends in the observations, and they are about 5 degrees in 80 years. So much, much bigger. Whether this is a problem with the observations or natural ability or the models being wrong. I mean, if you interpret 5 degrees would be substantial, right? I mean, that would be quite a shift, while 1 degree is not much of a shift, as I would think. So there's a bit of, they both go into the same direction. They are both widening, but the observations seem to be indicating that this might be much stronger than the models predict. Not sure whether you can trust the models or what the issue is here, but I'm just pointing out it's not a complete match, right? So they're both going the same way, but somewhat it looks like the observations might indicate that this is stronger than what the models predict. Okay, that much about the Hadley cell. Walker circulation, which I personally find more interesting because it's related to my research. Okay, so the Walker circulation is a sketch here. Here's Australia, South America. It tends to be warm here and cold here. And that induces, so this temperature gradient along the equator induces the solar circulation, which we call the Walker circulation. That means the air flows from the cold to warm. It rises over warm with lots of rainfall. We have this nice warm pool with lots of convection and rainfall. The air flows back, comes down here, and keeps it dry. So these kind of solar circulation cells here we call the Walker circulation. Basically, all of these branches are basically called the Walker circulation. And if the temperature gradient at the surface collapses, like during El Nino, when it's warm here and not that much warmer or equally warm here, then the circulation might collapse, and actually this uplifting or the rising air branch might be over the warmest temperature in the Central Pacific, and then convection is here, and then it's moist and rainy here, and it's dry somewhere else. So changes in this temperature gradient will have a big implication in terms of how the Walker circulation might be. Okay, so this Walker circulation is caused by these temperature gradients. So we have these warm temperatures here in the warm pool in the Indian Ocean and West Pacific, and relatively cold temperatures in the East Pacific, and also relatively cold temperatures in the Atlantic. And if there's a warming pattern in this as the surface temperatures in the future that is counteracting this, and this will lead to changes in the Walker circulation. Okay, so here's from a study from Bayard, and I'm one of the co-authors of it. It shows you the Walker circulation in terms of stream function. So we have here the surface, here's the dateline, somewhere this is the warm pool Australia region, South America, Africa, and this is the vertical, so surface and then to the stratosphere. And a positive cell means it circulates like this. So it goes here and goes up here, down here, and then. So this is a stream function telling you how strongly it is circulating. And this is centered over the Pacific. So this is the biggest cell, which we call the Walker circulation cell. And then the Indian cell is the other way around, circles like this. So it means there's upward motion here, here, and here, and then there's downward motion next to this in the downward branches. Okay, and then in the future, so contour lines here are now the mean state, and the shading is now the change in the IPCC models in an RCP 4.5 scenario. So it says that it becomes more negative, the stream function here, and the stream function becomes more positive here. So when the stream function becomes more negative here, it basically shifts the upward branch a little bit. Right? So it shifts the upward branch more into the center of the Pacific. And it shifts this upward branch more into the Indian Ocean. So there's a slight shift in the Walker circulation that the models predict. So this is plotted here in a diagram. So these are all kind of different models, CMIP5 models, CMIP3 models. Everyone has a different number here. And the blue dots and black dots are the averages of all these models. So on the x-axis is the shift in position in degrees, latitude. And to the right means El Nino-like. That means it likes to go towards the east. And to the left is La Nina-like. That means it goes towards the warm pool. And you see most of the models tend to be in this lower quarter here. And on the y-axis is the difference in the strength of the stream function. So a weakening of the stream function is down here, El Nino-like. And up here is the strengthening of the Walker circulation, which is La Nina-like. And you see most of the models tend to be in this lower quarter, and El Nino-like warming. And that means the warming pattern also at the surface temperatures is El Nino-like. That it means it warms more in the east than it warms in the west. So models tend to have a permanent El Nino-like condition in the future. Just for comparison, a typical El Nino looks like this, would be here. So there's a tendency for all the models to go into an El Nino-like state, but a moderate, not a strong, but a moderate El Nino-like state. So there's fairly good agreement. Yep.
Is this for a specific RCP scenario? Or?
Yeah, RCP 4.5. That is because most of the models have done this RCP scenario. But if you take RCP 8.5, it is the same thing, or 6. It doesn't really matter that much. They are all going to the same direction. But I think we took this one, or Tobias Bayer took this one, because there's lots of simulations in that. We took the one which is the most common one. Okay, so there's a very clear story here. I think models are predicting it's an El Nino-like change, so the Walker circulation will shift to the east a little bit and weakening. Unfortunately, this is not what we observe. In the last 30 years, the observations are off the chart here, up here somewhere, and they are in La Nina-like state. And this might be related to this, what people call the global warming hiatus. So somewhat the observations are currently doing something that is totally in disagreement. It's the opposite direction and in a big way. Right? And I think there's a mismatch. I don't know why there's this mismatch. I have no real explanation, but I would think that the models are doing something wrong. But I don't know. But there's clearly what is predicted hasn't happened yet. We have no way of telling yet whether these models are predicting the right thing. But I also would not rule out that this is true. Right? I mean, this can still happen. It might just be that this is an unusual observation, and the observations will turn around and then actually do what they should do.
Do you understand very well why the models do that? Is it ocean circulation change?
No. Nobody knows why. I think it's a big topic in El Niño research of figuring out how El Niño will change in the future. And there's a number of simple ideas of what could happen, but nobody really knows why or what happens. And at the same way, all these models have quite substantial biases. So one of the dominating things in El Niño is the Bjerknes feedback, so how sensitive is the atmosphere to SST changes in the wind changing to that, and these sensitivities are all wrong in the models. So a lot of the sensitivities, I don't trust the models, so I can imagine that they are doing something wrong. But it is really one of the things that's really not fully understood.
So they all calculate their own SSTs. They're not the same across the models.
Yeah. So they're all having the enzodynamics. They all have their own mean states. The mean states are having certain biases. So it's fairly well known that all of these models that simulate El Niño tend to have a cold tongue in the Pacific, which is too strong in general, and that changes the feedbacks of the models a little bit. And that might be one of the issues of the models, but we are not sure about it. Nobody can really say whether they are wrong or whether we should trust this. But I mean, I think the general idea is that we should trust this, and this is our best prediction. And if I have to make a prediction, I would go with this. But since I also know that the observations haven't done that yet, I have my doubts about it. And I actually published also a paper saying that the models are all wrong. So I have my doubts about that.
Is that due to the resolution, that cold tongue that's too strong in the eastern Pacific? Too much upwelling coming from...
Yeah, you can always argue that like that, but I'm not sure. I always think it's mostly in the atmospheric processes, like resolving moist convection and things like that.
Because the really coarse ocean resolution models tend to simulate upwelling that comes from too deep.
Yeah.
So that could be one.
Yeah, but I think it's the atmospheric forcing that makes them much worse, but we don't know really at this point. Yeah. But it's ongoing research, so it's definitely something that we have to look at. So this mismatch, I think, is really important, and it's relevant for Australian climate, of course. Okay, so summary, there are many different things, some of them well understood, some are not, and I haven't talked about all of these. I've just pointed out two main things, and that is the Hadley cell will expand by about 2 degrees in 100 years, and the Walker cell is predicted to weaken and shift to these, but the opposite is actually currently observed. So that's a bit of a puzzle. Okay, I'm totally running out of time, so I have to hurry up. Precipitation. Precipitation is, I think, more complicated than the atmospheric changes, so it's really tricky. But we have a simple starting point, and the simple starting point is the thermodynamics. So let's assume the circulation is not changing at all. There's nothing changing. Everything moves the same way as usual. Relative humidity is also not changing. Then you can simply assume from Clausius Clapeyron, if you have it should be plus 1 degree warmer, leads to 7% more moisture in the air. And that means you would expect an increase of 7% per degree warming in precipitation. Unfortunately, the models, again, makes it more complicated. It's only 3% of more precipitation per warming. So there's obviously something else happening. And since we started out with the idea that there's no changes in dynamics and humidity, that suggests that there might be some weakening in the circulation in the future. So that's the simple starting point. So we expect somewhat like 7% more rainfall per degree warming if nothing is changing, but it's less than that. So there's something is changing. So there's probably a weakening of the circulation. The second element of this simple thermodynamic idea of no circulation change is from Hadley and Soden. And that basically says that the changes in precipitation minus evaporation, they should be proportional to the mean of the precipitation minus evaporation. In other words, those regions which are fairly wet will get wetter in the future, and those regions which are fairly dry, so this is here equator, northern hemisphere, southern hemisphere, zonal averages, and this is the changes in precipitation minus evaporation in millimeters per day. So the wet regions get wetter and the dry regions get drier. That's basically the simple outcome here. If you don't know anything about it, you can assume that the wet regions get wetter and the dry regions get drier. And if you look at this pattern, Somewhere you see the wet regions, like the equatorial regions, get wetter, and the dry regions, the subtropics, get drier. So roughly, that's the first guess. Unfortunately, I'm running heavily out of time. But we can also see here that the points indicate that the models agree on the sign, and the lines mean they don't agree on the sign.